Okay, welcome back. This is now chapter 10 in Calc 2, 10.1. So we're going to have a lot of stuff that I guess we'll use in Calc 3. 10.1 is kind of a review, conics and calculus. And in particular, in Calc 3, we'll have three-dimensional objects like an ellipsoid, so something like this, where the cross sections are ellipses, which are just kind of circle-ish type things. Okay, maybe we can put the back of it in there. Anyways, we can define these three-dimensional objects in terms of their cross sections. Okay, so if you do a cross section, think of like that. There was an app a while back. It was like chopping fruit, and you chop the fruit in half, and you kind of look at it head on, and what's the two-dimensional cross section look like? And you kind of see it here. The kind of trace of what's left over is as an ellipse. So in this direction, if I cut it down, like I just slice it right there, I'll have an ellipse. And if you slice it in this direction, you'll have an ellipse. So it'll describe the object. There's going to be times where you're not going to be able to maybe draw it, but you can draw the cross sections. And not only that, you can do the formulas for the cross sections. So this section is kind of a review of those formulas. In particular, we'll see that the formula for an ellipse is just x minus h squared all over a squared plus y minus k squared all over b squared equals 1. There's some other issues along the way that the book is trying to get through to you. Unfortunately, we don't teach the 10.6 anymore, which was kind of the conclusion of all of this material. Basically, if you have an equation of a circle, something like x squared plus y squared is 9. To get the derivative of it, you would write y squared equals 9 minus x squared, and then you're kind of stuck with this plus minus square root thing. That's not quite a function, right? And even if you do just consider one hemisphere, it's still an annoyance to take its derivative and that sort of stuff. What this section would kind of lead into is the ability to redefine the conic sections in terms of a focus and a directrix. And then at the end, in chapter 10.6, the part that we're skipping now is, I forget the formulas, but I think they're like r of theta. So we redefine them in terms of polar coordinate system. R of theta equals E times, maybe it was D all over 1 plus or minus E sine theta or cosine theta. And then this guy's a little bit easier to handle than this guy. Well, that was always my kind of way of looking at it, but we're not going to bother with that too much anymore. All I want to do is kind of present these formulas and reminding you that these things are out there. You're going to see them hopefully once you get the Calc 3 and you're trying to figure out what graph you're dealing with based off of a formula. So not only that, you can get an idea of what the graph looks like by kind of letting one variable equal 0 and then looking at the cross-section formula, which are usually pretty identifiable as either one of the conic sections, so either a parabola, an ellipse, or a hyperbola. Right? Okay. So what are the conic sections then? Well, the circle is a conic section, so we presume you already know the formula for a circle. I just wrote one of them up here, but you have x minus, in general, x minus h squared plus y minus k squared equals r squared, where the center of the circle is at h the coordinate h comma k. All right. Then obviously the ellipse is kind of just a version of a circle. So it's kind of like an elongated circle. Okay? What else? Parabolas. The hyperbolas. And then we even have these other ones which don't get as much attention as they deserve. It's the degenerate conics. And these are like basic conics, like a point or just a pair of lines. Okay. So these things you'll see in the book, you can say that they're all results of kind of doing the fruit cutting game with this double-headed cone object. So if you were to split it down, like if you cut it like right here, the end result would be a hyperbola. Okay? So if you took a sheet of paper or something and kind of put it right through this part of the guy, so maybe I can try to draw it. We'll see how this goes. Not bad, I guess. So that's going to go up and kind of hit right here somewhere. All right, cat. Oh, all right. So something like that. And the trace on the paper is going to be these things here. So I guess I butchered this one. The top should be kind of like that. I should have practiced a little before I came in here. But that's the idea. And pretty much any of these can be formed by cutting this cone with a piece of paper in this sort of fashion. Okay? So if you cut it straight through the middle, you would get the pair of lines. You would just get this line and this line. If you cut it right through the middle, like with a piece of paper going right through it here, you would just get the point. If you cut it sort of at an angle, like maybe right here, and then the paper is going through it like that, you would get an ellipse. So okay, so that's that. We want to define these objects in terms of a set of points. It's a more loose definition than probably what you're used to, but let's take a look, okay? So first we begin with the most familiar guy, the parabola. And so what the heck is a parabola? A parabola is a set of all points such that we have these two equal distances, and I'll just call them PD equals PF. Okay? So here's a parabola centered at the origin, and we'll have a focus, a vertex, and then this directrix here. Okay? Then the actual branches themselves. Right? And you can define all the points on this curve here in terms of the fact that the distance from any point on the curve, so for instance this point P here, the distance from here to here, which is P to F, this is the focus, is going to be equal to the perpendicular distance from P to the directrix. So I usually call this point D. It's a perpendicular intersection there, and this directrix will have a formula x equals something. What is that something then? Well, traditionally we give the focus distance the letter p, little p this time, not to be confused with this big P up here. So this focus in this orientation is located at little p, comma, 0, and then the equation for the directrix is going to be x equals negative p. So the parabola is a set of all points such that the distance from P to the focus is equal to the distance from P to the directrix. Okay, so in general, what are the formulas here? In general, we kind of have some new formulas. Probably in pre-calculus, they gave you like a vertex formula and the standard formula, the quadratic formula, ax squared plus bx plus c. We want to define these in terms of this p-values. So you're going to see a p-value, and it'll kind of look like the vertex form that you saw in pre-calculus. Okay? So you have the sideways facing parabolas. Okay? So here you have this version with the directrix, and then this version with your directrix. For this version, this is when your p-value is greater than 0. This is when your p-value is less than 0. Right, the formulas then, like I said, they kind of look like your vertex form. You'll have a 4 times p sitting out in front of the x part. The way I kind of remember, which is squared is because in the form you're familiar with, it's always ax squared plus bx plus c, and this is kind of the reverse of that. This is kind of like ay squared plus by plus c. So you'd expect if the parabola is sideways to see the y variable squared. Okay? So from here you can get the vertex easily. So that's why I say it's a lot like the vertex form, h comma k, and then you use the p-value to kind of move back and forth from the vertex to identify your focus and your directrix. So the focus, I get that by moving in the x direction. So I need to manipulate the x coordinate of the vertex. Okay, so the focus is based off of the vertex. And then you just shift the focus according to the picture. Okay, so I'll be moving by p in the x direction, so x plus p. And then to get the directrix, you move minus p. You go in the negative direction there. So x for the directrix must equal h minus p. Okay? And this formula will work for both cases because when p is less than negative, this will become h plus something. So you'll be going in this direction, this positive direction, to get to the directrix. Okay, so those are the sideways parabolas. The parabolas we're used to, we have this shape. Okay, so let's put the directrix down here. And then we have, of course, the sad face parabola. Okay. This one is when p is greater than 0. This is when p is less than 0. I think it's always good to remind you, because in general, we're probably not going to be using these formulas in Calc 3. You're just going to be using your standard formulas that you learned in pre-calculus. And the standard formula for this guy would be y equals ax squared plus bx plus c. And I want to remind you, how do I find the vertex for that? It's h equals negative b all over 2a. And then f of negative b all over 2a, but which is the other coordinate, right? That's the k coordinate. Okay, so anyways, just a reminder, the formula that they're working with in the book, though, is just basically this formula with the x's and the y's swap-swapped. So x minus h squared equals 4p times y minus k. This time, to get to the foci, you're moving up to get to the directrix, you're moving down, and you're manipulating the y-coordinate of the vertex. So again, the vertex is h comma k. The focus is just a shifted version of the vertex, right? And in this case, because we're going up, we're going to be manipulating the y-coordinate. So I'll be adding p to the y-coordinate. Over here, you did left and right, so you added it to the x-coordinate. Then the directrix will be y equals, and we have to move down to get to the directrix. So I'll be taking k and then subtracting away p. Right, so let's take a look at maybe one in the book. This, you know, it's has the completing the square flavor to it sometimes. Find the vertex, focus, directrix, and then graph the thing. So we have y squared minus 4y minus 4x equals 0. Okay, so this looks like it's going to be one of the sideways parabolas because this thing is squared. I'm going to move the x material to the other side, and I'm going to have to complete the square. So I'm going to go plus blank, and over here 4x plus blank. The blank is always going to be this thing all over 2 squared, assuming that you have a leading coefficient of 1. Right, so negative 4 all over 2 squared is negative 2 squared, which is 4. So I add 4 to both sides to complete the square. Then you factor, so you get y minus 2 squared equals, and I want to get it into my form, 4p times x minus h. Right, so I can factor out that 4. My vertex I could read directly from this formula, so it's negative 1 comma 2. You just take the opposite signs. The 4p is equal to this 4 part. Okay, so it's just a coincidence that this is 4, and you know we have 4p in the formula. So I have to find my p value. So you take 4p and you set it equal to whatever is sitting in front of this binomial. Okay, so in this case it's 4. In other words, p is equal to 1. The p-value is positive. The form is, you know, like this. So I'm moving in the x direction to get to the focus. So the focus should be negative 1 plus 1 comma 2. And then the directrix x should be negative 1 minus 1 and negative 2. So now we just go over there and graph the thing. So my vertex is negative 1, 1, 2. Get my focus, I'm moving it 1 in the x direction, so over here. To get my directrix, I move 1 in the other direction, so over there. And then you can use, what is it? It basically just graph the thing. I just do a sketch. There's other things you could do, something called a lattice rectum and stuff like that. I don't bother with that too much. Unless I'm teaching pre-college or pre-algebra or something, and then I'll teach it. But here, I think a sketch is just good enough. Knowing you're dealing with a parabola, you know, that usually tells you 90% of the information you need to describe a three-dimensional object. Okay, so in general, you're not going to be able to, or you're not going to want to take time to learn how to sketch three-dimensional objects. So you can kind of consider them in terms of the cross sections, and that gives you a good idea. Okay, so anyways, there's that. Let's look at ellipses now. So the second sort of conic section that we care about in this section is the ellipse. It's basically just an elongated circle. And again, we define it in terms of distances. And in this case, the formula, there's going to be 2 foci. So it's going to be the sum of the distances to the foci is equal to a fixed constant. Okay, and that fixed constant is 2a. The a is an actual value on the graph. So if we do the graph here, I'm going to put some points so we can draw the thing kind of. Okay, so here's our graph. Traditionally, these things are the vertices. Okay, the long part of the circle is called the major axis. The short is the minor axis. Right? Half of it's the semi-major axis and the semi-minor axis. This point here is the vertex, and you're always going to give it the coordinate with the letter A. So in this orientation, it's at the location A comma 0. The foci are inside the ellipse, and this guy over here, this vertex. So there's two vertices. This is negative A0. Okay, the coordinates for the foci will be in terms of C. So this is negative C0, and then this foci is at C comma 0. These points on the minor axis are going to be given in terms of B, as in beta. So the top guy would be at 0B, and the bottom guy is at 0, negative B. Okay, so if you take any point, arbitrary point on the ellipse, the sum of the distance from here to here plus the distance from here to here is equal to 2a. All right, so maybe I should label this. This is vertex 1, this is foci 1, this is foci 2, this is vertex 2. Okay. And yeah, so I mean that's the deal. This distance, but so sometimes people describe it in terms of a piece of string. So you imagine a piece of string attached at foci 1 and attached at foci 2, and then you kind of pull it as far as you can to some point. And then if you keep it taut, you can kind of scratch out the form of the ellipse. Okay, so you take a piece of string, tack it down here, take it down here, and then push it out as far as you can, and then sort of scribble it in, and you end up with the ellipse. Okay, anyways, in general then, the formulas, and we'll have two orientations to deal with. So there's this kind, and so maybe we have it in the first quadrant. You'll have two foci, two vertices, and then these guys on the up and down here, and then a center here in the middle. So the formula for this thing is going to be x minus h squared all over a squared plus y minus k squared all over b squared equals 1. The formulas for the center, the center first off is the h comma k. That's the middle here. And then to get to the foci, you're going to move left and right. So you're manipulating the x coordinate of the center. And what distance do you use? You use the c distance. So where is the c value in this equation? You don't know where it is. You can always find c by saying c is equal to the square root of a squared minus b squared. Okay, and this means in general that a has to be greater than b for the ellipse. All right. This formula it's kind of has that Pythagorean feel to it, and it's because you can generate it just by thinking of a right triangle at this. If you put this p at this position, you form a right triangle that has sides a, b, and c, and then you could solve for c. Okay. Okay, so that's where that formula is from. Anyways, to get to the foci, let's do the vertices first, right? So there's two vertices. And usually we just write them at the same time. So vertex 1 and 2, you're going to move by the value a. Okay, so first you manipulate the x coordinate of the center. So x plus a comma k to get to here, and then x minus a plus k. So we're just going to write x plus or minus a comma k. For the foci, then, it's the same deal, except you're going by a value of c. So it would be h plus minus c comma k. And then we have these other vertices, and I just call them minor vertices. So I write v sub m because they're on the minor axis. The book doesn't really give them a name or anything, but I want you to draw those if I ask you to. So in those cases, I'm manipulating the y coordinate of the center going up and down, and the value is that b value. Okay, so I'll have h comma k plus or minus b, as in boy. Okay, let's look at the other version then. So we have this more of a up and down orientation. The vertices are on a line parallel to the x-axis along with the foci. There's our center, and then our minor vertices on the sides like that. The formula is kind of, in practice, it's hard to distinguish this formula, but the deal is the variable that has the bigger number in the denominator tells you which form you're dealing with. Okay, so in this form, yeah, it'll be y minus k squared all over a squared, but obviously you're not going to know which is a and which is b unless you know this fact, that a is always greater than b. So anyways, y minus k squared over a squared plus x minus h squared all over b squared equals 1. Again, the center is given the title h comma k, but now I'm going up and down to get to the vertex and the focus. So instead of manipulating the x coordinate, I'm manipulating the y coordinate. So my vertex, my vertices will be at h comma k plus or minus a. So I have to go up and down. Then my foci will be h comma k plus or minus c. And then finally, the minor vertices will be at h comma k. Whoops. So I'll have to be moving left and right to get to those. So it'll be vm h plus or minus b comma k. All right. So that's pretty much the spiel for that stuff. One thing we're probably not going to worry too much about is eccentricity. If we were going to go on and do 10.6, eccentricity would become important. In astronomy, if you're doing that kind of work, and it seems like that kind of work should be more prevalent than it was when I was a kid. You know, you can't imagine, I could never imagine working on satellites or something. That would be crazy. I would have been locked in an institution at that age. But now it seems like with cell phones and stuff and communications the way they are, it seems like it's almost possible to get a job working with satellites. I'd probably have to join the Army or something, but I don't know. It seems, I don't know, it seems like the closer we get to working with satellites, the less actual, you know, hey, let's not do 10.6 anymore, even though it used to be kind of out, there. Now it's more realistic. We're going to stop teaching 10.6. Anyways. Oh, I'm gonna have to have a talk show. Okay, so number 27, 9x squared plus 4y squared plus 36x minus 24y plus 36 is equal to 0. So standard issued kind of formula for this scenario. And Calc 3, instead of having a 0, maybe you would have a z over on this side, and you would let z equal 0, and that would be essentially looking at a cross-section of a three-dimensional object. Right? But and then you would have this object, and you'd be trying to figure out what this is. Right? So you're going to have to complete the square twice on this one. So I have 9x squared plus 36x plus, then get the y parts, so 4y squared minus 24y, push the 36 to the other side. And then to complete the square, you need a leading coefficient of 1. So I'm going to factor this 9 out of these two terms. And you'll have x squared plus 4x plus blank, and then plus 4 times y squared minus 6y plus blank. On the other side, negative 36, right? All right. So what goes in the blanks? Well, and there's one other thing, right? I need to add this stuff to the other side, but I need to be a bit careful. Whatever you add in, you're not just adding in the blank. You're adding in the blank times the 9, right? Because if you distribute it over here, you get 9x squared plus 36x plus 9 times whatever you're putting in here. So you've manipulated this side of the equation with something times 9. So over here, you have to be a little bit careful that you also have it multiplied by 9. So what am I saying? Here, 4 all over 2 squared is 4. Okay, I can't write 4 over here. I have to go 4 times 9. Okay, so that's 36. This case, 6 over 2 is 3. 3 squared is 9. And again, I can't write 9 over here. You have to write 9 times 4 is 36. Okay, so I completed the square. Now you factor. And get it into your form. So divide everything by 36. 9 over 36 is 1 over 4. 4 over 36 is 1 over 9. And I have 1 over here. So in these problems, you have to identify A, B, and C. It's kind of your first step, like the p-value for the parabolas. And in particular, then, the A value is the bigger value. Right? So it's not like they're going to give it to you with the Y thing first if that's the orientation, right? It's going to be mixed up. So here, the A value is actually the 9 because the A has to be bigger than the B. So it's 3, and that tells you the orientation is this type, okay? And then the B value is 2, so this is B squared. Another mistake you can make, don't write 4. This is B squared, so you write 2. And then C is the square root of 9 minus 4, which is square root 5, which of course is around 2.2. Okay, you can kind of graph it, and you know, probably want to know the vertex, the center. The center is -2, 3. Okay, so -2, 3. I'm in the. I should have gave myself more room over here. I'm in the second quadrant. Right, so I'm sitting right here, and then to get to the vertices, I'm moving up and down. Okay, so my vertices, I'm manipulating the y coordinate. It'll be 3 plus or minus 3. Okay, so I can go over here and 1, 2, 3 up, and then 1, 2, 3 down. Okay, for my vertices, my foci, again, you're going up and down, so -2, 3, and you're using the C value this time, plus or minus root 5. Okay, so 1, 2.2-ish, 1, 2.2-ish. And then finally, for the minor vertices, you're going left and right by the B value. Okay, so -2 plus or minus 2, 3. Great. So 1, 2 is right here. 1, 2, put me right there. And then finally connect the dots and you have your ellipse. Okay, great. The last kind of conic section then is the hyperbola. Again, we're going to define this thing in terms of a set of points that fulfill some distance formula. So section 4, the hyperbola. And at this time, it'll be a set of all points such that the difference of the distances to the foci is equal to a fixed constant. Okay. So let's look at a particular case centered at the origin. Okay, for these, you're gonna have A, B, and C values again. The A values again will give you kind of the vertices. The foci, so this point would be a vertex. This is a vertex. The foci this time are on the outside of the vertices, okay, which is a little bit different. And you're not going to have, well, what is this thing? It looks like two parabolas, basically, and you form them off of a kind of a box that you'll draw. So the minor vertices, again, are up and down here. So V sub M1 and V sub M2. How do I draw this thing? Well, first you get these 4 points, and then you draw a box. Okay? And then you're going to put asymptotes through the box to help guide the branches of the hyperbola. Okay? Okay, so the hyperbola is going to be this thing, That's one branch, and then over here you get another branch. Okay. So this PF1 and PF2, what are those? Well, you take an arbitrary point on the curve that's labeled P. The distance from P to F1 is minus the distance from P to F2. You take the absolute value of that, you get this fixed constant 2a. Okay, so that's the definition of the hyperbola. Let's look at the general forms and the equations. Okay. So in general then, we have two orientations again. So I always draw a little box and then do my isotopes, okay, and then my vertexes, and then my foci, and there's my branches. Okay, so the formula is pretty much just the formula for ellipse, but with a minus in between the terms. So you'll have x minus h squared all over a squared minus y minus k squared all over b squared equals 1. Okay. Then you need to, the center is going to be at h comma k, and I believe the formulas are all the same as they were for the ellipse. So to get to the vertices, you're just moving left and right by a, so it'd be h plus or minus a comma k. To get the foci, you're moving left and right by c, so h plus or minus c comma k. And then to get to the minor vertices, which aren't actually even on the graph, sorry, my stupid crud. Then to get to the minor vertices, okay. So to get to the minor vertices, you're going up and down, so you're manipulating the k coordinate by b. Okay. Okay, so what is the c value this time? And there's no restriction on a and b. Okay, so before for the ellipse, a had to be greater than b, but not this case. You can tell the orientation by which term is negative. So when y is negative, you have this orientation. When x is negative, you have this other orientation that I'll draw here. Okay, but anyways, the c value this time is going to be the square root of a squared plus b squared. Okay. Right, so the other orientation then that we have is where the branches are up and down. So I'll draw my box, put my points on there, draw my isotopes through the center. And then the branches, there's one on top, and then there's one on the bottom. Right, so the formula this time has the y term being positive as opposed to the x term. That's how you tell the orientation. It's not the a and b values this time. So y minus k squared all over a squared minus x minus h squared all over b squared equals 1. Center again is h comma k. And then to get the vertices now, you're moving up and down. So you're manipulating the k coordinate. So it's h comma k plus or minus a, and then the foci are at h comma k plus or minus c, and then those minor vertices on the box, you're going left and right to get to those. So those will be h plus or minus b comma k. Okay. All right, so let's look at 37. My camera, and there it is. Okay, so 37, again, it's kind of given to you in scrambled form. So if this is multivariable, this would be equal to z. And then to get an idea of its cross section in the xy plane, you would let z equal 0. So you're kind of projecting it onto the xy plane. Right, so this thing will become then, let's see, I got to reorganize. So it's x squared plus 2x, and then I'm going to have to complete the square. And then for this, the negative 9y, and I'm going to have to factor out a minus 9, and then get y squared plus 6y plus blank. And on the other side, I have 80, and then I have to go plus blank plus blank. B all over 2 squared. So 2 over 2 is 1, 1 squared is 1. And here, 6 over 2 is 3, 3 squared is 9, so I get minus 81. Okay, so factor, so I have x plus 1 squared minus 9 times y plus 3 squared. On the other side, I have, 0. Right, so, what does that mean? This is one of the degenerate conics, okay, and it happens. You can still get the formulas for the degenerate conics. You just have to kind of do a square root. So add this dude to the other side. You x plus 1 squared equals 9 times y plus 3 squared. And then do square root property on both sides. So you have x plus 1 equals plus or minus 3 times y plus 3. And then you could separate this into two equations. X plus 1 equals 3 times y plus 3 for one of the lines. And then the other line is going to be x plus 1 equals negative 3 times y plus 3. And if you want to draw it, you can get solve it for y. So, 3y plus 9 is x plus 1, 3y equals x minus 8, and then y is x over 3 minus 8 over 3. And then over here, negative 3y minus 9 is x plus 1. Negative 3y is x plus 10. Y is negative x over 3 minus 10 thirds. Okay, so you see these have one is falling and one is rising, right? So if you drew it, I'm not going to take time to get crazy about it, but you're going to get an x. Okay? You'll get this guy, which is, again, it's one of our degenerate conics. Okay, we want to look at these one or two applications here. So section 5, some applications from the book. And so the first one, I have 65. There's this pipe which is going through kind of a curved reflector bin. So maybe the reflector bin is heating the pipe. Okay, so I have this sort of, let me try to draw it here. Okay. Okay, so there's, I don't know, this is all right. So a pipe going through here, and then this is a curved reflecting plate, and maybe the sun is coming in and then heating this pipe. We want to make sure that the pipe is at the focus of the parabola. That way all the light beams will come and reflect into that pipe. Okay, so what is the distance to the directrix, the focus. So first what we could do is kind of redraw it so we have the straight on view, right? So if I kind of tilted it over and then looked head on, it would be a parabola. the book is telling us that it's the distance across the top here is 6 units. So this point would be at 3. And then the depth from the top to the bottom is 1 unit. I want to know the distance to the focus, where I should be putting the pipe. Okay, so basically you need to know these distances here from the reflector to the pipe. So how do I do that? Well, you could play with in this orientation, it's going to be x minus h squared equals 4p times y minus k. It's centered at the origin because what we did. You could center it wherever you want, but this is the easiest place to center it. So you get this expression. We need to figure out the p-value in order to get to the focus. So, excuse me, we're going to plug this point into this equation, and then we get 9 equals 4p times 1. So p must equal 9/4. Okay, so the distance to the focus then is going to be 9/4 unit from here to here. Another question, 73. We're given some information about the orbit of Earth around the sun, and we're modeling it with an ellipse. Okay, so the sun is at one of the foci, and then the Earth is flying around it. So let's put the sun there. It tells us our eccentricity is 0.0167, and it says 1/2 the major axis is 149598000 kilometers. Okay. It wants to know the perihelion and the aphelion. So the perihelion is the closest the Earth gets to the sun, and the perihelion is the furthest the Earth gets from the sun. Okay. So I did give you that formula for E earlier. I didn't say we said it's mainly used in 10.6, but I guess we use it here. The method for doing this is to kind of collect the A, B, and C values, and then we should be able to do it. I don't even think we need the B value, honestly. It's just this A and C value. So at least here we can kind of get an idea of one in terms of the other. And then 1/2 the major axis is the distance from here to here. Okay? And traditionally, if you look back in your notes, we called this point is going to be at location A, 0. In other words, 1/2 the major axis is the A value. Okay? So I have a relationship between A and C, and I actually know A. That means I know C. Right? So C will equal A times the eccentricity. So if you evaluate that, it's going to be, well, I don't know what it's going to be, 149598000, 8,000, whatever, 149598123 times the eccentricity of 0.0167. Okay, great. So the perihelion and the aphelion. So for the perihelion, that's the distance from the sun to this further vertex. So you can put it in terms of A and C's, right? So this distance is C. Then we have this distance A. So the perihelion is going to be A plus C. Right? And then we can rewrite that as this plus this, and then you can factor out the big ugly number, and you have 149598123 times 1 plus the eccentricity. And then for the aphelion, it's this little distance here. So that's this big distance A minus this little distance C. So A minus C is aphelion. And in this case, we just have a minus instead of the plus. Okay. That's it. All right, so I think that'll do us for this section. We'll see you next time.